question we're interested in answering is, how do we calculate the area between a function curve and the x-axis? When a function does not have any concavity, calculating the area between the function curve and the x-axis is just a matter of identifying what polygon is formed. So for example, if we have a constant function, which is a horizontal line, and we're interested in calculating the area along the interval from A to B, we see that a rectangle is the polygon that is formed, and therefore, to calculate the area between that constant function and the x-axis, it is a matter of identifying the base and height of this rectangle to get the exact area. Another example, let's say we have a linear function with an identifiable slope and y-intercept. And again, we're interested in calculating the area between the function and the x-axis from the interval from A to B. In this case, you'll see that the polygon that is formed is a triangle. So calculating that area is still a matter of identifying the base and height and using the correct area formula for the triangle. If I change the interval in which we are trying to calculate the area for, say instead of A to B, we are now going from C to B, we'll see a new shape is formed, and that is a trapezoid. So calculating its area is using the trapezoid area formula, identifying both bases and its height, and that will get us, again, an exact area representation that we're looking for. The point of the examples I've shown so far is that we can get an exact area between the function curve and the x-axis if the function itself has zero concavity. So we had a constant function and a linear function, which do not have any bend in the actual curve. The only example where if we have concavity, we can definitely get an exact area formula at this point with the tools that we have at our disposal would be, say, a semicircle. So if we had a semicircle, we know we can just apply an area formula for half a circle, so half pi r squared. So in that case, we could get an exact area calculation for something that does have concavity. However, if we have a function that is not a semicircle and has concavity, how do we get the area between the function and the x-axis? We're going to use approximation method. So for example, if I draw this function concave up, and we're still interested in finding area from A to B, we'll see that the polygon, or there isn't a polygon that's formed, but the shape, I should say, that's formed is something like this. And calculating that area, we don't have a formula for. So what can we do? Well, we can approximate the area by using shapes that are familiar to us and easy to calculate areas for individually. So it would be a wise option to break down this shape into little rectangles and calculate the area of the rectangles to get an approximation. So to show you what I mean, let's say I take the interval from A to B and we use 4 rectangles to approximate the area. Now you can see in this case that these 4 rectangles, if I calculate the area of each and added them all up, we would get an under approximation. There's still some gap between the rectangles I've drawn and the actual function itself. So it's not exact, but it is an approximation. And with a little foresight, you could probably guess that the more rectangles you use, the better the approximation. So the smaller that green space will become. So more rectangles, better approximation. As the number of rectangles approaches infinity, then we'll get actually an exact representation for the area between the curve and the x-axis, but that's further down the line. So all we're interested in now is how we get the best approximations, or what methods we can use to approximate area under a curve. So let's jump over to 3 methods using rectangles. We have LRAM, we have RRAM, and we have MRAM. LRAM, left rectangular approximation method, RRAM, right rectangular approximation method, and MRAM, midpoint rectangular approximation method. So we'll use the same function so you can clearly see the differences in the visuals for all three. And we're still working from A to B. And let's use 3 rectangles for our approximation for the area between the function and the x-axis. And again, the more rectangles you use, because we're set on a designated interval from A to B, the more rectangles I introduce, the smaller their width is going to be. And we're going to jam pack a bunch of rectangles into that space, thus getting a better and better approximation. So let's say we're using 3 with the left, and let's say we're using 3 of equal width. So let's make these sub-intervals within the entire interval. So equal width rectangles or base values are the same for LRAM on this individual sub-interval, and we'll label these points. Let's call this x sub 0, x sub 1, x sub 2, and x sub 3. And we'll use x sub 0 or x naught to stay consistent with notation that indicates an initial starting point. So we'll label the same for all. And we're going to use 3 rectangles of equal width. For an LRAM, when I look at this first individual subinterval, so from x sub 0 to x sub 1, you take the left endpoint of that subinterval, go up or down to the function, whether it's above or below the x-axis, intersect the function itself, and then go horizontally over to the other endpoint of the subinterval to create your rectangle. Repeat for each subinterval, so take the left endpoint, go to the function curve, go over horizontally to the other endpoint of the subinterval to make your rectangle. So repeating this process, you'll see there are 3 rectangles. We can even mark off the additional space to show the full area we're trying to approximate. You'll see again there's a gap between the rectangles and the function itself. So this case is an under approximation. But for an LRAM, something to keep in mind if you're drawing it out visually, the top or bottom left corner of the rectangles intersect the function curve. Okay, so we're using left endpoint for each subinterval. So bottom or top left. It could be bottom left if the function is below the x-axis. RRAM is what you might expect, that instead of using the left endpoint, we're now going to use the right endpoint of our subinterval to go up to the function, over horizontally, repeating this process. So the top right, or bottom right corner of our rectangles are now intersecting. In this example, you'll see that our rectangles give an over approximation for this function example. So that's not always going to be the case, and we'll look at that later in the video. But for this case, over approximation. MRAM is taking the midpoint. So now, rather than using the left or right endpoint of the subinterval, we have to calculate the midpoint on each subinterval. And once we identify the midpoint, or that point right in the middle, that is the point in which we go up to the function curve for our intersection. And once we hit that, we go horizontally to create our rectangles. So it is the midpoint of the subinterval that provides us with the height of each rectangle. So there are just 3 examples, illustrations of those 3 methods. But let's make a more generic conclusion as to how we calculate an approximation using LRAM, RRAM, and MRAM, or how do we get the areas of each individual rectangle. So the width for each example, the calculation will be the same. And let's say we're working along a subinterval. We're going to call it x sub k to x sub k plus 1. Okay, so this is just looking at an example subinterval and how you calculate the area for that rectangle on that subinterval. And at the end, what you would do is once you've calculated all the areas, you just add them all up. So if we just observe one example abstract subinterval, we can carry on this idea to all the other subintervals. So x sub k to x sub k plus 1. So what are the k values? K is going to be an element of the set. It's going to start at 0. You can see the points that we've marked to make our subintervals in green on the examples above go from x sub 0 to x sub 1. So if we start at 1, think of plugging in 0 for k. We have x sub 0, and the next point when we add 1 would be x sub 1. So that would mark our first subinterval. And this goes up by 1, and it goes as far as n minus 1, where n is the number of subintervals. Now, why do we stop at n minus 1 as opposed to n? Well, if you plug in n minus 1 to x sub k, so say we want 3 subintervals in total. The last subinterval you can see in the example here is 1 less than n, so it's going to be 2. And then when we add 1, we get to our final result, 3, which is n. Or if you plug in n minus 1 and then x sub n minus 1 plus 1, because k is going to be n minus 1 to n, you'll see that the plus 1 minus 1, we just end at x sub n, or the very last point. So we want to stop at n minus 1 for the values of k. Okay? And again, n represents the number of subintervals you want, and it can be heading towards infinity to get your best approximation. So we're working along, this just represents an individual subinterval along the entire interval from A to B. First, to calculate area of a rectangle. To get the base, or the width. Fortunately, it's the same calculation for all 3 cases. We're just finding the length of the subinterval. So we're going to take x sub k plus 1, and we're going to subtract x sub k. And again, what does this mean? Interpretation, just find the length of the subinterval. You might not even have to do the mathematical calculation out by hand. You can probably just do it in your head, but we're just trying to find the length of the subinterval. How do we get the length of the height? This is where things change for each example. The length or height of the rectangle comes from the function output at one of the endpoints or the midpoint, depending on what example we're looking at, for that specific method. So length, height. Let's break these down into 3 categories. We'll see for LRAM, for RRAM, and for MRAM. For LRAM, to get the height or the length of the rectangle, again, we're working on that imaginary subinterval from x sub k to x sub k plus 1. We just evaluate the function at the one on the left, which would be x sub k. For RRAM, we're going to evaluate the function at the one on the right, which would be x sub k plus 1. For MRAM, we're going to evaluate the midpoint. How do we get a midpoint? Often it's easy to identify if the values are simple that represent the endpoints for the interval. You just find the value right in the middle. But if things get a little more complicated, the general formula, we're going to add together the values that represent the endpoints of the subinterval and divide by 2. We're just averaging. Okay, so we'll make a little note here. That just represents the average of values that represent the subinterval. And again, this x sub k plus 1, we can see that this is our left and this is our right, and we're working up left to right, least to greatest, so we know we're working in the correct direction. Let's also make a note here. So that's how you find each one, and then you just multiply them together. So ultimately, it's just taking the function output Again, which function output you use depends on what method, and then multiplying it by the length of the subinterval, and there's your area for that individual rectangle. And then at the end, make sure to sum the area of all rectangles used to get approximation. So don't just stop after doing one. And we want to note about this function output. Let's make a little note here. Just in general, a good thing to know that if we take a function output at some point C, geometrically, this represents the height above, we'll say of the function at x equals c above or below the x-axis. So it's telling you the distance. So maybe we'll make a little note for height. Distance from the x-axis, okay, or the height from the x-axis that function is above or below. So a little side note, good thing to know. The geometric interpretation of a function output is the height above or below the x-axis. So those are your three rectangular approximation methods. All right. There's another approximation method that we can use, which is the trapezoid method. So now instead of using rectangles, we're going to use a different shape. Let's look at the same exact function as we did before. Let's still work in that same region from A to B. And let's use 3 trapezoids. The difference here is to draw the trapezoids on your individual subinterval. Both endpoints go to the function curve. So we just immediately draw a line up to the function curve from all endpoints of the subintervals. And then what we do is just connect the intersections with a line to form these trapezoids. Now, to use the trapezoid approximation method, we need to know the area formula for a trapezoid. And it is 1/2 the sum of the bases times the height. Now, the one thing we want to pay attention to with this method is with the rectangles, the height was the function output. But in this case, the function outputs will represent the bases of the trapezoid, because on a trapezoid, the bases are the sides that run parallel to each other. And you can see in this image drawn here, the sides that run parallel to each other represent the actual height above the x-axis, which is our function output, as we just discussed. So B1 and B2 are going to come from the function output at the endpoints of the subintervals. So how do we get the height? The height of an object is an altitude from a point to the base, from a highest point to the base, I should say. So an altitude runs perpendicular from the highest point to the base. So a line that runs perpendicular to the base is the subinterval along the x-axis. So these run perpendicular to the bases. So we wouldn't want to use that slant height, but rather, again, that side that runs perpendicular to the bases. So this is going to be found by just finding the length of the subinterval. So base and height gets flipped with the trapezoid method, something you want to pay attention to. So now, let's look at the generic way to calculate the trapezoid area for just any subinterval. So we'll say along subinterval x sub k to x sub k plus 1 again. And we want to note, we want to make sure we establish what the values of k are. So k can range from 0. Again, we marked off the subinterval values. We went x sub 0, x sub 1, x sub 2, x sub 3. And the reason we started x sub 0, another convenient thing that occurs when we start from x sub 0 is the last number in the subscript for the final subinterval represents the number of rectangles or trapezoids that you're ultimately using. If we started at 1, then the last number would be 1 greater than the number that we're using. So it's nice to start at 0 for that reason as well. We're counting by ones. And it's going to go all the way up to n minus 1. Again, because we established that the subinterval from the abstract form is going to go from x sub k to x sub k plus 1. So we want n minus 1 to be the stopping point so that the final value is x sub n, which n is equal to the number of subintervals. So along this height, we marked off in red, that should be the length of the subinterval. So how do we find that? We're just going to find the difference between the two values. Okay, and the order matters here. So we want to do greatest to least so that we get a positive value here. Okay, if in doubt, we can put absolute values around it. But you'll see later that when we actually learn to calculate an integral, you'll see that the order actually does matter, and it changes the sign of the area and all that stuff. So we want to pay attention to that. For now, let's go greatest to minus the least value to make sure we get a positive output. Now the bases. So base 1 and base 2, we are going to be calculating the function output at the endpoints of each subinterval. Okay, that gets us base 1 and base 2. We plug in the values of the subinterval into the function to determine how high above the x-axis the function goes or how far below the function goes from the x-axis. Once we have those pieces of information, we plug it into our area formula, and that is the area for one of the trapezoids. So again, make sure at the end to get your approximation, we want to add or sum together all trapezoid areas for the approximation. So make sure you finish the problem, don't just use one. Okay, so those are the three methods. Or sorry, that's 4 methods in total. 3 rectangular approximation methods and the trapezoid method. And to end the video, let's take a look at how do you know which method is better than the other? Or if you're asked to use a certain method, given a certain type of function, do you have an over approximation or do you have an under approximation? When it comes to LRAM and RRAM, let's actually just look at 2 examples. All you care about is if the function's increasing or decreasing. Okay? If the function is increasing, then LRAM will be an under approximation. So we can see, for example, that an increasing function, those LRAM rectangles, you see there's the gap below, so this is an under approximation. We're going to say LRAM under approximation. But for a decreasing function, LRAM is an over approximation. You can still see, again, the top left corner of our rectangle is intersecting the function. So this is an LRAM representation. So LRAM over approximates when we have a decreasing function. Now when it comes to RRAM, it's the exact opposite. So RRAM, we'll see that the top right is supposed to intersect. So when it's increasing, RRAM shows an over approximation. RRAM on a decreasing function, we see an under approximation. This is when f of x is increasing, f of x is decreasing. So whether or not you have an over approximation or under approximation for the LRAM or RRAM methods, that's all dependent on whether or not the function is increasing or decreasing. If you forget it, just draw out the example, or just draw out a picture. Say, okay, I know f is increasing, and then just draw an example LRAM, and you'll see that it's an under approximation. But when it comes to the trapezoid method, we don't care about whether or not it's increasing or decreasing, but instead we care about the concavity of the function. So let's look at something that's concave up versus something that's concave down. So in this case, both functions are increasing. So let's take a look at the trapezoid method now. If we use the trapezoid method on an increasing and concave up, you'll see that the trapezoids are a slight over approximation. But if we use them on something that's concave down, we're going to get an under approximation. Okay. So there's a slight gap above the bending of the function when it bends up, and there's a slight gap below when you bend the function down. So for trapezoid method, again, you're considering the concavity, not whether it's increasing or decreasing. We can see here an example of two functions that are increasing, and we have an under approximation and an over approximation. So we have to look at the concavity instead. So for the trapezoid method, concave up, we have over approximation. And then for concave down, we have an under approximation. And again, this is one of those things where if you forget, you can draw out an example to illustrate the point. So there are your approximation methods, and at the end of the day, it is just a matter of calculating the area of familiar shapes from your geometry class. So you're just breaking down the interval into rectangles or trapezoids, and then summing the areas of each individual rectangle and trapezoid to get an approximation for the area between the function curve and the x-axis.